So thank you, James. And I would also like to thank the organizers of the conference, Professor Chung Ji, Professor Wen, for giving me this opportunity. Today, I'm going to speak on Light-Front Maxwell Chern-Simons Higgs Theory, the Broken Symmetry Phase. And in this talk, I would first of all recapitulate the model in the symmetry phase. So and I would discuss its instant form and light-front quantization. And then I would discuss the same model. I would present the same model in the frozen or broken symmetry phase. And also I would discuss instant form and light-front quantization of this model. So it's a model of electrodynamics in two-space one-time dimension, which involves a Maxwell term, a Chern-Simons term, and a term that describes coupling of the U1 gauge field with the complex scalar field in the presence of a Higgs potential. This theory could also be considered as an abelian Higgs model in the presence of the Chern-Simons term and a Higgs potential, where the kinetic energy of the U1 gauge field is given by the Maxwell term. And these theories in 2+1 dimensions can describe particles that satisfy fractional statistics. So these particles which satisfy these statistics are generally known as anyons. And this Chern-Simons term has a remarkable property that it depends only on this antisymmetric tensor epsilon mu nu lambda and not on metric tensor g mu nu. So what happens as a result, this Chern-Simons action in the flat and the curved space is same. So this action in both the abelian and non-abelian case, this represents an example of a topological field theory. And the solution of these Chern-Simons theories, they play an important role in a better understanding of the relativistic models of fractional statistics and anionic superconductivity. Now, the theory which I'm going to present is a constraint system, and these systems with constraints, they play a very important role in the description of fundamental laws of nature. In fact, most of the systems which have physical importance, they are constraint systems. So for example, electrodynamics, quantum chromodynamics, electroweak theories, string theories, and also de Bruijn actions, they are all constraint systems. And there is a classification of constraints by Dirac. So according to that classification, these primary constraints are the constraints that follow directly from the Lagrangian when momentas are inexpressible. So this means they are independent of velocities, and the preservation of these primary constraints, that this gives us secondary constraints, and the time evolution of just a minute. And the time evolution of these secondary constraints, this leads to tertiary constraints and so on. However, we call all the constraints other than primary constraints as secondary constraints. And further, if the matrix of Poisson brackets among these constraints is singular, then this means that the set of constraints is first class. And if it is non-singular, then we say that the set of constraints is second class. But if the matrix of Poisson brackets among the constraints is a null matrix, then it represents a pure or a bona fide gauge invariant theory. But sometimes if it is not null, but it is singular, even then theory remains a gauge invariant theory, but it possesses some Gauss anomalies. And sometimes these Gauss anomalies, they increase to such an extent that the matrix becomes non-singular, then theory loses its gauge invariance. Now, the Dirac bracket of two dynamical variables A and B, we use the following convention in 2+1 dimensions. And here, these gammas are the constraints of the theory, and this delta is the matrix of Poisson brackets among the constraints. And this is our convention for the Poisson brackets among two variables, A and B, in 2+1 dimensions. And finally, one can make transition to quantum theory by writing down this Dirac quantization rule, where this Dirac bracket goes to minus I times commutators. So here A hat and B hat are now quantum mechanical operators. Now the theory is defined by the following action or by this Lagrangian density. So where this Lagrangian density is a combination of three terms. So this term, first term is the electromagnetic Lagrangian, and this second term is the matter Lagrangian. And this third term is the Chern-Simons term. So this first term is the kinetic energy term of the U1 gas field. And the second term, this represents a coupling of the U1 gas field with the complex scalar field, as well as the kinetic energy of the complex scalar field. And this describes the Higgs potential. And the fourth term is the Chern-Simons term. And this Chern-Simons term provides a velocity-dependent gas field. And the presence of this Maxwell term in the action, this makes the gauge field dynamical. And we take the following form of the Higgs potential, and we choose the parameter of the potential in such a fashion so that the potential remains a double well potential, so that here the spontaneous symmetry breaking takes place. That is, ground state of the system is not invariant under the U1 symmetry of the system. Also, we can write this in this form where phi 0 is not equal to 0. D mu defines the covariant derivative. This one is the complex conjugate of d mu. Theta is the Chern-Simons parameter, and kappa is defined by theta over 2 pi square. This is our G mu nu is our metric, and this one is antisymmetric tensor. And of course, mu nu takes values 0, 1, and 2. Now, this theory, without this Chern-Simons term, this is an abelian Higgs model and is defined by this Lagrangian density. When these models are considered without this term, but only with this Maxwell term, where this Maxwell term accounts for the kinetic energy of the vector gauge field, then they represent field theoretical models which could be considered as effective theory of Ginzburg-Landau type of superconductivity. And in 2+1 dimensions, this theory is known as Nielsen-Olson vortex model. And this Nielsen-Olson model is, in fact, a relativistic generalization of the well-known Ginzburg-Landau model of superconductivity. And this Ginzburg-Landau model is a phenomenological field theory model of superconductivity. Also, most of the time, these models, quantization of these models is a challenging problem. And a simple possibility for defining a quantum theory is that we start with a classical theory and then we quantize it. And basically for this, there exist two equivalent approaches. So the first one is called canonical quantization or the Hamiltonian quantization given by Dirac. And the other one is given by Feynman path integral quantization. So in this talk, I would present a consistent Hamiltonian and path integral quantization of this theory in both the forms. Now, first of all, let us come to the theory in the symmetry phase, where we study this theory, and in instant form, where we study this theory on the hyperplanes defined by the instant form time x0 equal to constant. So for this, first of all, I express this Lagrangian in the component form, and then I look for the momentas of this theory. So here pi star, pi 0, E1 and E2, they are the momentas canonically conjugate to phi star, A0, A1 and A2 respectively. And we can see here that this momenta is inexpressible. So corresponding to this, there exists one primary constraint in the theory. And this symbol here, this denotes a weak equality in the sense of Dirac. And it implies that these constraints, they hold as a strong equalities only on the reduced hypersurface of the constraints and not in the rest of the phase space of the classical theory. And similarly, one can consider it as a weak operator equality for the corresponding quantum theory. Now, by use of the Legendre transform and by using definition of momenta, we write down this canonical Hamiltonian density of the theory. And then after including this primary constraint chi1 in the canonical Hamiltonian density, with the help of this Lagrange multiplier field U, we write down this total Hamiltonian density. And this is our total Hamiltonian. Now, when we project this primary constraint in the course of time, then we get one more constraint. So this is our secondary or Gauss law constraint. And the matrix of Poisson brackets among these two constraints, this comes out to be a null matrix. So this implies that this theory is a gauge invariant theory, and it is in fact invariant under these local vector gauge transformations. And in this, vector current is conserved, so everything is fine. Now I come to the Light-Front theory. So for the Light-Front, we define this light cone coordinates x plus x minus as 1 over square root of 2, x0 plus minus x1. And then what we do, we rewrite all the quantities which are involved in the Lagrangian density of the theory in terms of x plus x minus instead of x0, x1. And also this a minus plus upstairs equal to a plus minus downstairs equal to this 1 over square root of 2, a0 plus minus a1, and delta plus phi equal to 1 over square root of 2, delta plus phi plus minus delta minus phi. So in the Light-Front quantization, we quantize this theory on the hyperplanes of the light front, which is defined by x plus equal to constant. So this is in contrast to the instant form where we study this theory on the hyperplanes defined by x0 equal to constant. And actually this idea of quantizing on the light cone as a characteristic surface is given by Dirac, who called it front form of dynamics as opposed to the usual space-like surface quantization. Now for the Hamiltonian formulation of this light front theory, first of all, we express this Lagrangian in terms of light cone coordinates. So here I have expressed this Lagrangian in terms of light cone coordinates. And now we look for the canonical momentas of the theory. So here pi is canonically conjugate to this capital phi, pi star to capital phi star, pi plus to a minus, pi minus to a plus, and e to a2. And now in this one can make out that these first, second, third, and fifth, these are inexpressible. So therefore, corresponding to this, the theory has these four primary constants. So these are our four primary constants. And then we can we write down this total Hamiltonian density of the theory by including these primary constants with the help of Lagrange multiplier fields, this W1, W2, W3, and W4. And then we project this first constant in the course of time, and then we get another constant. But by preserving other constraints in the course of time, we do not get any new constant. Instead, we get a condition on the Lagrange multiplier field. So this is a total set of constraints. Okay, these four primary and one secondary. Then further we make the linear combination of these constraints, omega 2, omega 3, and omega 5. So this gives us a new constraint, and I have renamed this constraint as omega. Then again, I have renamed all these constraints. So Xi1, Xi2, and Xi3. Then these constraints, Xi's, form a set of first class constraints. So this theory represents a gauge invariant theory, and the vector gauge current is conserved in this theory. And now in order to quantize this theory using Dirac's procedure, so one has to convert these first class constraints of the theory into the second class constraints. So for this, we need some extra conditions. So here I have used this one extra condition, which is called gauge fixing condition. So here A minus equal to 0 represents the light cone time axial gauge. Now this choice of gauge fixing condition gives us four constraints. So, and then we calculate the matrix of quadro brackets among these constraints, and then we see that now it is non-singular. And so the set of constraint is now second class, and the theory becomes a gauge non-invariant theory. So I have written here these non-vanishing elements of the matrix of quadro brackets among these constraints. Now for the Dirac quantization, we need the inverse of the matrix of quadro brackets among these constraints. So these are the non-vanishing elements of the inverse of the matrix of quadro brackets among these constraints. And then I follow this Dirac quantization procedure. And then we have calculated these results. So these are among the canonical variables. So between phi, pi, phi star, a minus pi plus, a to e, a plus pi minus. So now this was the theory in the symmetry phase, and I reported these light cone results last year. Now I come to the theory in the broken symmetry or in frozen symmetry phase. So this was our theory in the symmetry phase. Now I come to the broken symmetry phase. So for this, I set this phi equal to 1 over square root of 2 phi 0 exponential of I phi. So and here this where phi, this is the phase of this complex matter field capital phi. So the phase phi carries the charge degrees of freedom of the complex matter field, this capital phi, and it is in fact akin to the Goldstone boson. Now, in this broken symmetry phase, what happens? This potential looks zero, but it is zero only here at the circle of contact, and everywhere else it is non-zero. Algebraically, also, if you set in this potential, this phi equal to constant times exponential of I, where phi, then it comes out to be exactly zero. So in broken symmetry phase, the symmetry is frozen here. Therefore, it is also known as frozen symmetry phase. And in this broken symmetry phase, this one minimizes the Higgs potential to its minimum value by freezing the scalar field at the degenerate minima of the Higgs potential, and the phase of the complex matter field, this where phi carries the charge degrees of freedom of the complex matter field, capital Phi. Now in broken symmetry phase, our Lagrangian looks like this, and here one can see that the potential is not even visible. So it looks zero, so this means it is frozen to its minimum value. And now if you multiply these two terms, then you will see that you get one term here, which is the mass term for A mu. So vector gas boson A mu becomes massive in this broken symmetry phase. Perhaps this mass generation takes place through a mechanism which is similar to the Higgs mechanism. So, and this, because of this mass term, gauge invariance is lost. So gauge invariance breaks down here, and now I express this Lagrangian in, first of all, I consider this instant form. So I write down this Lagrangian in component form. And then we write down this canonical Hamiltonian density with the help of this Legendre transform and by using definition of momentas. So this one is our canonical Hamiltonian, and this one is the total Hamiltonian by including this primary constant with the help of Lagrange multiplier field U. And now again we look for the canonical momentas, and here this capital Phi is canonically conjugate to where phi, and pi 0 to A0 as before, E1 is conjugate to A1, E2 is conjugate to E2. Now in this theory there exists one primary constant, and when this primary constant is preserved in the course of time, we get one more constant. And then again, if we preserve this constant in the course of time, we again get a new constant. But when we again follow the same procedure, then we get a condition on a Lagrange multiplier field. So this theory has only these three constants. And then we can combine these two constants. So we have combined these two constants. So altogether, theory has only two constants here. And now if you calculate the matrix of Poisson brackets among these two constants, then it comes out to be a non-singular matrix here. So this means we can calculate the inverse of this matrix, and the set of constants is now second class, and this theory is a gauge non-invariant theory. So we have calculated these Dirac brackets for this theory. So these are the Dirac brackets for this instant form theory. So this is between phi, bare phi and pi, A0, pi 0, A1, E1, A2, E2, A0, pi, and also all of these brackets, A0, E1, A0, E2, A1, A pi 0, and so on. And now I come to the light-front quantization of this theory in the broken symmetry phase. So first of all, I write down this Lagrangian density in terms of light cone coordinates. So, and then I look for the canonical momentas of this theory. Now here, capital Phi is canonically conjugate to where phi, and this pi plus is canonically conjugate to A minus, pi minus is canonically conjugate to A plus, E is canonically conjugate to A2. And now by looking at it, we can make out that here these first, second, and this third one, this fourth one, they are independent of velocities. So corresponding to this, there exists primary constants in the theory. So these are the three primary constants of the theory. And then we write down the total Hamiltonian density of this theory as we have written earlier. And then we preserve this primary constant, first constant in the course of time, then we get another constant. This I have renamed it omega 4, but the preservation of other two constants, for example, omega 2 and omega 3, this does not give rise to any further constants. So theory possesses these four constants, and this forms a set of first class constants. So theory is now becomes a gauge invariant theory. And now vector gauge current is conserved in this theory. So in order to quantize this theory using Dirac's procedure, we need some gauge fixing conditions. So I have taken, for example, here these two gauge fixing conditions. And here, this gauge A minus equal to 0, this represents the light cone time axial gauge. And this E equal to 0, this represents the light cone Coulomb gauge. So now with these gauge fixing conditions, altogether, this is a set of constants. However, this choice of gauge fixing condition is not unique. In principle, we can choose any other gauge fixing condition that would convert the set of constants of the theory from first class into a set of second class constants. However, it is always better to choose such type of a gauge fixing condition that is physically more meaningful and more relevant, like the one we have chosen. So for example, here we have taken this gauge fixing condition, and this represents the light cone Coulomb gauge, and this one represents the light cone time axial gauge, and both of these are physically important gauge fixing conditions. And another point which I would like to mention is that one cannot choose covariant gauge fixing condition here, simply because the constants of the theory are not covariant, and therefore it would not work. Now, the matrix of Poisson brackets among these constants is now non-singular with these gauge fixing conditions, and that the set of constants is now becomes second class, and theory becomes a gauge non-invariant theory. So I have written here these non-vanishing elements of the matrix, and then I have written here the inverse non-vanishing elements of the inverse of this matrix. So, and then following the standard Dirac quantization procedure, one can calculate the non-vanishing equal light cone time Dirac brackets of this theory. So these are the equal light cone time Dirac brackets of the theory. And each one of these, this requires a lot of calculation. This is really a lengthy calculation. Now, for the path integral quantization for this theory, one can make the transition to quantum theory by writing down this vacuum to vacuum transition amplitude, which is called the generating functional Z of the theory. So in the presence of the external source JK, for example, I have written here, this is functional measure of the theory, and this is exponential times this IS, where S is the action of the theory. So this one is the action, where this one is the first order Lagrangian. And these 5 Ks, they are the phase space variables of the theory. They are the corresponding momentas of the theory. And this one is the total Hamiltonian density. Now the functional measure of the theory d mu of the generating functional Z under this gauge fixing conditions can be written here in this manner. Here, this capital D, this is the square root of the absolute value of the matrix of the Poisson brackets among these constants. So I have written it here, and this involves all the variables, all the momentas, and also constants of the theory.
Sorry, Usha, just to give you the 3-minute warning before the question session. Thank you.
Thank you. Thank you. So this completes the Hamiltonian and path integral quantization of the gauge invariant theory in the broken symmetry phase. Now there are certain advantages of the Light-Front quantization over the instant form quantization. So for example, despite certain technicalities, this front form dynamics often turn out to be a simpler one and more transparent than the instant form without giving up on the net physical contents. And also this Dirac pointed out in his famous paper, Reviews in Modern Physics, that in particular, this Light-Front form remains invariant under 7 generators of the Poincare group, while the other 2 are invariant only under 6 of them. And in the Light-Front quantization, there is no conflict with the microcausality principle, because these Light-Front coordinates are not related to the conventional instant form coordinates by a finite Lorentz transformations. And so the description of the same result, this may be different in instant form and in Light-Front quantization of the theory. And in our context, in Light-Front quantization of field theory models, we have seen that a theory which is gauge anomalous in the instant form, this is no longer gauge anomalous in the Light-Front form or Light-Front quantization. So we found that this Maxwell Chern-Simons Higgs theory in the broken symmetry phase is gauge non-invariant in the instant form of dynamics. However, it becomes gauge invariant in the front form of dynamics. So I come to the summary that we have considered instant form quantization and the Light-Front Quantization of the Maxwell Chern-Simons Higgs theory in the symmetry phase of the Lagrangian, symmetry phase of the Higgs potential. And we have studied this theory in the broken symmetry phase, and I have presented instant form as well as the front form quantization of this theory. And I have seen that in broken symmetry phase, the theory is gauge non-invariant in the instant form, and it is gauge invariant in the front form. And also, we have discussed the quantization in the instant form and in the front form. So thank you.
Thank you very much, Usha, for this very comprehensive discussion of the comparison between instant form and front form with this interesting 2+1D theory and your comments on other theories as well. This contributes a lot to the body of knowledge, growing body of knowledge about equivalence of these the physics in different quantization schemes. I see Philip has his hand up. Philip, would you like to ask a question?
Sure. Ush, thank you very much for the presentation. I just want to make one very small comment. While it's true that the transformation from instant to light front is not a Lorentz transformation, it is a space-time dependent translation, which is also a general coordinate transformation. So if you're working in a theory which is general coordinate invariant, then you must get the same answers, whether you work in instant time or in light front time. And Daya mentioned the big review that Stanley, Peter and I wrote. Once you recognize that you have a space-time dependent translation, then light front and instant become unitarily equivalent. and that's what makes them, that's why they all work. Because if it were different, you'd have a big headache, which is the one that describes nature. So they have to be equivalent. And that's one of the things that we work through.
Mm-hmm.
Thank you, Professor Manan, for the comment.
Are there other questions from the participants?
Usha, you wanted to tell us about the multiple convolution integrals?
So if I have time, then I can just show this one calculation involving this multiple convolution integral. So these Dirac brackets. So for example, I have calculated only one Dirac bracket. So here I have this pi minus A2. So this is equal to, first of all, this term. So this is the Poisson bracket. Then minus times this term, and this term. So I have called this first term, this whole term I have called second term. This one I have called third term, and these three are called fourth term. So, and then I have calculated one by one. So first term is the Poisson brackets. So I have calculated this Poisson bracket, and this comes out to be 0. Then in the second term, because this one is 0 here, Poisson brackets, so therefore this second term is also 0. But this third term, for example, here, this third term is a combination of these two terms. So I have calculated first B1, and B1 comes out to be this one. So I have used all these. First of all, I calculate Poisson brackets among these constraints. Then I use this inverse of the matrix elements, and then we write down this. So in 2+1 dimensions, because these variables, they increase, so it becomes difficult to calculate. Then it comes out to be B1 equal to this whole thing. So I have used definition of delta, delta prime, epsilon, etc. And then I get this one. And then the second term, similarly, I calculate. So similarly, I calculated the second term, and this second term, we get this one. And then I have calculated this fourth term, which is a combination of C1, C2, and C3 means 3 terms. Then again, I have calculated these 3 terms. So C1, C2, and C3, and I get this. And then we add all these terms. So I have added all these terms. So I get this long bracket in this long Dirac bracket. So
That's a lot of hard work there. Thank you very much.
yeah, it's sometimes in two, for example, if space variables are more, then it becomes difficult. Then you have to keep track of all the variables here and there.
Very good, very good, very good. Well, there's a lot of interest, of course, in having these equivalences shown. It's not so easy, obviously.
Yeah, most of the time I saw only results. So I thought, let us write down one Dirac bracket.
Great. Thank you for your hard work and clear presentation. We've come to the end of our time.